Greetings, everybody. It's my pleasure to present our work on behalf of my co-authors and colleagues. My name is Marina Tavra. As we well know, and Mr. Gomez already said enough about it, 80% of all world data contain location component, and we could name such data spatial if we transform their location in format that is machine readable. And in this presentation, I will talk about preparing data for geoanalysis. It is for recovery and after disasters crisis phases, but it could be useful for part when we can develop some system in the case of real-time applications. Who we are? Briefly, we are interdisciplinary team from University of Split. Currently, we are working together on several projects related to various cases of crisis management in general. This is the core of our team. We also have several associates from different organizations related to emergency, crisis, and disaster management. We also have a good collaborations with other universities, as also as University of Ljubljana in Slovenia. I will talk about use of user-generated content in crisis presented on two case studies. The first case study is transforming social media posts into volunteer geographic information using data mining methods. Volunteer geographic information versus crowdsourcing, we can all use on another workshop about that theme. And the second case study is a missing person search area prediction based on volunteer geographic information and remote sensing data. The first case study is about fire occurrence in Croatia. Beyond the scope of traditional geospatial data collection, we can say that individuals can now collect the data through a new concept of a volunteer from 2007. Good Child first mentioned this concept as volunteer geographic information, and isn't that new, but it's new in informatic era. VGI is often described as a subset of crowdsourcing that includes activities of voluntary collection of data that contain or could retrieve a geospatial component. VGI contributors are typically non-experts who may collect data explicitly or implicitly in terms of topology, describe geographic information. In explicit type of VG data, the geographic location are immediately defined. In the implicit type, we extract its location from the data, images or text, posts on the social media, social networks. The implicit type of data collection provides a much greater opportunity to use the data and has a different approach to evaluating and preparing the data for geospatial analysis. An example of VGI used in this research is textile posts about the fire from the social media Facebook, social network Facebook. The first step to make this kind of data usable for geospatial analysis is geoparsing, which consists of geotagging and geocoding. Geotagging is a process of adding geographical identification metadata, and geocoding is the process of taking a text-based description of a location, such as an address or name of a place, and returning geographic coordinates to identify a location on Earth's surface. Motivation and goals. This study aims to answer the two main research questions. Is it possible to automatically and effectively transform social media posts containing unstructured text into VGI? And the second, would VGI be more beneficial than plain text posts in terms of insights and analysis in disaster management? In this paper, we present the process of converting social media data into geospatial data in the case of use Facebook post about fire in Croatia over a 5-year period. The research was conducted on a sample of almost 5,000 posts, parsed and filtered using different geocoding algorithms. We present the transformed VGI data on a map revealing the areas that are mainly covered by the user-generated data. Finally, we demonstrate how the VGI with the geospatial component can give us insight into geospatial density of disaster using example of the fires that occurred between July 16 and 18 in 2017. We created a script to filter posts and download only those that match up with keywords fire, burn, and intervention. And it is important to emphasize that the text of the post were written in free format, unstructured, often using dialects with numerous typos and grammatical errors. Some text processing was required to identify the required parts of the text. The toponyms, also known as a place name or geographical names, words that refer to geographical location. We used a list of Croatian settlements as a list of known toponyms and searched for the most similar word occurrences in the post text. I already said something about methods. We assumed that social media posts text related to fire incident mentioned the toponyms of the settlements in which event they are referred. Known toponyms at the settlement level were extracted and geocoding is also performed at the settlement level. This figure showed on the slide shows complete geoparsing workflow, which consists of the two main activities, geotagging and geocoding. Geotagging can be referred to the text mining process where toponyms are retrieved using named entity recognition. Named entity recognition is one part of natural language processing that can help identify entities that are crucial for extracting information from the text corpus. In this case, toponyms from a set of social media posts. And this slide shows the cartographic process model as a general methodology for representing the distribution of fire events based on geocode textual social media posts. The input data social media posts are geotagged and prepared for georeferencing, and we use two geocoding systems, paid and free, to compare the results and usability for the disaster management of this approach to georeferencing. Results: when we look at the comparison of spatial distributions at the settlement level, we see similarity that show the effectiveness of identifying places where an incident took place. These mechanisms work comparably to already established special databases, so that the results often depends on the amount of data in the integrated databases. S3 at the right results in terms of geocoding speed proved to be fast, as the Republic of Croatia was chosen as the geocoding area. When we use a free system called Nominatim by the plugin of QGIS, this possibility does not exist, so it took more time to run the algorithm on the global scale. The direct correlation between the occurrence of the fire and the number of published posts about fire is indisputable, and there is a consistent evidence that may be broader all through the smallest unit for geocoding and measuring posts, in this case settlement level, can suggest where is a greater possibility of fire in both cases of geocoding, which is confirmed by EFIS data of actual fires. After displaying the distribution of the posts only originated from that period, we can see the special distribution of the VGI that is concentrated around several settlements. This corresponds to the burnt areas recorded by the EFIS systems, visible in the comparison of geocoding results and EFIS data. This example proves that the automatic transformation of social media posts into VGI or crowdsourcing and displaying the VGI distribution, we can gain into intuition about possible occurrence of disaster without any further analysis of the text. And this study showed that the unstructured social media post can be automatically transformed into implicit VGI and effectively used in disaster management. Case study number 2 is an extension of the study titled Lost Person Search Area Prediction based on the regression and transfer learning method. I would not talk about the model. I will present the short version of this study, and we are currently in the process of writing paper based on this study, so I can't talk about that too much, but we can discuss it. It would be glad to we will be happy to discuss it. Okay, in this case study too, authors construct algorithms of optimal areas for lost person search, having in mind the initial point of planning and features of the surround area. The algorithms are trained on previous search and rescue missions data collected from 3 stations of the Croatian Mountain Rescue Service. The training was performed in 2 training phases and having 2 data sets. The first phase was the construction of a regression model and of the speed walking, and this model predicts the speed of walking of a rescuer who is considered as a well-trained and motivated person, since the model fit on dataset made on GPS tracking data. The second phase is the calibration of the model for lost person speed of walking prediction with transfer learning on lost person data. The model is used on the simulation of walking in all directions to predict the maximum area where a person can be located. This diagram shows the pre-processing data steps where the GPX set contains GPX files. Each file consists of a trail of one person walking. This trail is a record of the series of geographical points where a person is wearing a GPS device was walking. These were processed and transformed into segments. Segments describe walking between 2 points and an Earth surface. Each segment is described with a start and end point as well as a start and end time. From this information, we can easily calculate the necessary features of a segment, distance length, the slope of terrain, and the speed of walking segment. And the method is demonstrated for terrain in Croatia and proposed for use as a part of the decision support system for search and rescue missions. Special distribution of GPX files data are collected from 3 mountain rescue service departments, Split, Karlovac, and Dubrovnik. The trails are collected in a wide area of 3 cities. The resulting area is irregularly shaped, and the shape depends on the configuration of the surrounding terrain. This means that in the direction where the terrain is configured so that one must walk slower, the area search to be is smaller. The search area defined in such way is more accurate than the traditional approach. Determination of the radius of a circle around the initial point of the search where every direction is probably the same, while still do not reject area where the probability of finding a lost person is low. In future, we will extend this work, and in future work, we will include other features into account in refining the model, remote sensing data and data from other sources, such as weather data. We are now working on inclusion of remote sensing data, where we could by included this slope of the terrain, we will include the land cover layer. And to achieve a better precision of the predictive model. We hope that it will be one predictive model that we could, in new cases of the lost person, we could predict a map of searching using that remote sensing data, and also including forest roads or vegetation that where one person could be lost. Conclusion, it's a little bit two case studies that are from other side, but we can conclude for each or for both that data from additional sources such as user-generated content can contribute significantly to decision support in disasters or crises. And with information retrieval focusing on geocoding data and the quality, at the end, we can obtain different including different databases or considering the semantic of mentioning unstructured text, and the proposed methods are different from others in the field of geocoding or lost area person predict. It doesn't really focus on the accuracy of position, but it considers the broader picture of obtaining spatial patterns using text mine methods. In the first case, the data set can be enriched with additional data sources. In first case, it could be population, and already said in the second case, it would be weather or remote sensing. Thank you for listening, and feel free to contact me or co-authors.